Hello together. Now we want to make the next exercise for the pressure drop flow field pipe simulation cases. At first we want to look at our exercise sheet, and here's the exercise. We want to create three different geometries of pipes, and we want to measure pressure drop inside these pipes, and want to compare it with the pressure drop values in the table here. Okay, let's start the lectures. At first I go to full screen again, so that you can see everything. So perfect. I think that's a good choice now. And let's start with the first geometry of this pipe. It's a rectangular pipe with a special diameter, and you have two bows here inside this. Okay, so we are back on the ANSYS Workbench, and it's a student version 2020, and we start with Fluid Dynamics CFX and the toolbox, and I can create geometry, net, you can set up solution and results. And here I see we have the German version, so maybe that's not so convenient for everyone. We want to change it back. We go here to original settings, to English. Okay, and now we have to restart again. I go to OK, I close it. We don't have to save it because it's not much done yet. And here again I go back to ANSYS, the R2020 version. Okay, wait a sec. It's here. And now we start again the ANSYS 2020 version. Okay, and after this restart we should have the English version now, and we go again to fluid flow problem. We put it on the project schematics, and now it's in English language. It's geometry, mesh, setup, solution, results, and we start our first geometry with the design model. So please don't use a double click here. Go to the right mouse button and click it. Okay, and here now the ANSYS Workbench starts. We can see the design modeler, and we choose a plane, X, Y, Z, X, Y, Z plane, maybe like this. And we want to create a rectangular pipe, not a pipe, more a channel. And first thing we have to do a sketch, and we choose XY plane, and we sketch here a rectangular, maybe like this. Maybe don't fix it in the 0 point, just throw it here over the whole domain. It's a bit big. I undo it. I zoom in a bit. Let's have a look on the data, how big it was. Okay, it doesn't matter, we can choose any size. So let's choose, for example, as a diameter, let's say 10 centimeters, and we choose our rectangular like this. And now we have to define the dimensions. We go to horizontal. It's about, let's say 0.25 meters. Oh, that's okay. We have to make it a bit bigger. To make this bigger, we go to modify, drag, and we drag the box a bit bigger, and then we go back to dimensions and choose the next dimension. Again, I choose a horizontal dimension, click on the axis, click on the edge, and again I choose 25 centimeters. Okay, doesn't look really rectangular, so I have to go to the vertical dimension. I double click and make it bigger, and the last step is I do an additional vertical dimension, and again I choose 25 centimeters, and now we have a diameter of 0.5 meters. Okay, that's our first diameter of the pipe system of the channel. And now we look back at our exercise. It should have this geometry here. Yeah? It should have rectangular and 90-degree angle, and we need here a pathway. Okay, so I do this first step. I go back to modeling and I choose another plane. For example, the YZ plane is really convenient now, and what I need now is a line for the pass. The pass I want to choose for my pipe, and before I do it detailed, I draw it a bit with a pencil and make sure the pencil head is always connected here. You should always connect the pathways before you choose correct dimensions. And let's check it. Make it generate from time to time. Check it. Go to, you have now sketch 1, the pipe diameter, and sketch 2, the pathway for the pipe. And now we can use this swap feature here. You see it in the top of the menu. It's called the swap feature. We can swap the pipe. You go to swap, you choose your profile, that's on sketch 1, it will be highlighted in yellow. You go to apply, and then your pathway is still yellow. You go to sketch 2, again to apply, and now you see the profile and the path in light blue color, and here you see this little swap symbol, and there's a small flash on the swap symbol. I go to generate the swap, and here you see our first pipe system is finished, and it is gray highlighted. Looks quite well, looks quite nice. Okay, that's fine, but I think the dimensions are not really correct. Let's go back. What is written here, unfortunately in German, but you can maybe translate it a bit. You see the length of the pipe should be here about 2 times dimension of the diameter, and this part of the pipe should be about 3 times of our diameter. Okay, so our diameter have been 50, though we make the length of this edge 1 meter. You just go to dimensions, horizontal, like this, or vertical was the right choice. Go to vertical, and you reduce it from 2.2 to 1 meter. Again, if you have done this, go to sketch to get the right geometry. Okay, next step is we need a vertical dimension, and this should be 3 times the diameter, so it's about 1.50 meters. I go to horizontal, I choose a sketch, and it's not so bad. Let's say 150. Okay, it's pretty cool, but does not look as it is a 90-degree angle. This will influence our result, so we need to choose here also 150. Go to generate from time to time, and this vertical should be also 1 meter. Okay. Yeah, is it okay? Do you think it is okay for you? Diameter 3 times diameter. Is there a bug? No. We have, maybe we make this a bit longer. You can now easily just change it in the table. Oh, that's too long. Let's try 150. 150. Have a look. Is this correct? Okay, I think that's not so bad. 3 times D. D. I know. Here's one little bug, because and that's important for the result later, I have to make this a little bit shorter, because I took the middle point here, so I have to change this to 1 meter and this to 1 meter. Generate. Now it looks a bit better, and we change this also to 1, 1, and now it looks pretty cool, like our result. It's finished, but not totally finished. We need some boundary conditions, so we go back to the modeling tool. We choose here this modeling. We go to this named selection. We apply it, and we go to the second, to the exit. We again choose a named selection. We applied it, and so we have 2 named selection. And what is a good name? For example, we take here inlet for inlet flow, and outlet for outlet flow. We go back to generate. It's check it from time to time. It's fine, it's finished, it looks good. And now we can close the design modeler. The design is already here. We can go to save now, and now take care. This is geometry number 12, so I want to take the same name later here on the workbench, but here first I have to give a name to my simulation, and I call it on the simulation, and I want to call it height simulation, or let's pressure drop. Pressure drop simulation. That's a cute name. Let's check the mesh, or maybe I explained something about the mesh last lecture. It works automatically. You can generate it even if you don't enter the tool, and you can have a look into the folder. So let's have a look. Mesh should be already finished. Okay, from time to time that is window message, and this is a cute mesh, maybe a bit coarse. We can make it a bit finer, quality a bit better. Let's have a look. So we insert here a sizing method. Again, we choose a whole geometry and we make element size. Maybe before I choose it, I go to generate. Element size is fine. And I make it a bit smaller. Okay. Now the mesh is final and it is a nice hexaedral mesh. There's no need to make a tetrahedral mesh or something like this. Also the named selections, inlet and outlet are defined. It's pretty cool. And before we want to go to the meshing, before I start the simulation, I open my PowerPoint and make the first screenshot of the mesh to keep it. Yeah, maybe design is not so nice. We can take a much nicer design, for example this one. It's a good design. And we take the first picture of the mesh to show what we've done later. But it's a good time to make a screenshot now. Okay, make it a bit smaller, crop it, then I'm much faster later. Okay, just keep it, go to save it. Okay, I close the file, I save the project, go again to update here to get a mesh into the workbench, and then I go to setup and go to edit, and then I make my edit. Okay, this is a standard Windows message from the firewall. Just go to allow, and here is my geometry. You see the mesh, it looks good. Here's also my default domain, and I go to insert inlet, and I choose the inlet. It's also done automatically, and this can choose now the inlet file, and I need now a velocity, because, or let's say, yeah, I take a let's say I take a mass flow rate, and I have yeah, it's about ½ meter size, so I can, and I want to make a simulation with water later. So let's say how big should we do the mass flow? It's not given in the exercise. I have to decide my own mass flow, but mass flow rates maybe not so good. I take these velocity components and I take in Z direction 1 meter and 0, 0. Now I have an inflow of 1 meter at this inlet. That's easy to calculate later. If I calculate the brush drop and I go to OK. Okay, now at this point maybe that's a good chance to look at how to calculate the pressure drop. And I've copied you in the Moodle a help for your exercise. Here you can see it. In this exercise, here's the pressure drop. It's we have our sheet component that is also in the table. We have lambda, but because they are smooth walls, we will set lambda to 0, and so we have rho, the density divided by 2, and velocity squared. So we need velocity, and later can formulate or measure our pressure drop and formulate our shear value. Okay, we will come to this point maybe a bit later on, and come back to ANSYS. So if we want to calculate pressure drop, we need one velocity as a boundary condition, and then we take for the other boundary condition a pressure. That's important. Don't take a velocity at the exit or a mass flow, otherwise you will not get any senseful values. And I choose 1 bar at the exit. It's like an opening to the outside here. Okay, an opening might be a good idea, because I don't want to choose an outlet. I want to choose an opening, because it's not totally defined if everything flows out of this pipe or if there's a small swirl in the pipe. Okay, and then I can rename all the other walls. Very simple. And I use smooth walls. So I want to set lambda to 0 later walls. Okay, and the simulation maybe go to 100 here to get comparable results. Okay, that's it. Perfect. We're finished. It should run. Give it a try. I hope the compiler will be fine. Before you start the numerical solution, go to Save, go to Solution, Update. Again, here is this message from the firewall of Windows. Doesn't matter, just accept it, and the solution starts to run. During the run, I can check a bit. Okay, convergence is not so fantastic, but it doesn't matter. Never mind. Let's have a look at the result. And now we can edit the results and have a small look. Again, firewall asks us something, and we go to the post processing steps. The results are here. Perfect. And the first thing I want to do, I want to plot a nice string trace from the inlet to the outlet, and it looks pretty cool. It is a right result. We can take this result. It's fine, and you see what can you see here? We will have an influence of the geometry on the flow. Yeah, we have a swirl region here. We will have a swirl region here. To make the visualization a bit nicer, we can also choose a renderer here, like this. So, to make it look a little bit nicer, 0.7 is always a good value for transparency. And that's our first pipe result, looks pretty cool. And I want to make a plot here. And I make the next screenshot when it's open. I copy it to the board. So looks pretty cool. First geometry is finished, and let's call it pipe .12 because it started with a 12 in the table. .12, 13 and 14. Okay, we will do it, fix it later on. Looks still pretty cool. Yeah, it's good to see. Make it in the right color. Don't forget to save it from time to time. Okay, now we come to the next. Now we come to the next step. Here's the velocity, and I see the stream trace. It's pretty fine, but we want to have some more. We want to have a look at some more features, and there's also this contour plane feature, where you can sketch a contour plane into your YZ. Maybe like take a 0. Place it in the middle. Okay, and I switch off the streamlines. I have a plane inside my object, and now I can choose a color here at the plane and add as a brush. That's a pretty fine picture. We can also make visualization of the velocity. Look like this. If you take conservative, it's even better. And we can make a nice sketch of our velocity distribution. You see we have pretty fine velocities. We enter with 1 meter per second here at the bottom, but at the exit we have swirl regions. We can also see some mesh quality problems, but never mind, just take it like this. Make a screenshot. If you press here, you can rotate it like this. No. Okay. Or if you press Control and you use the left mouse, you can rotate it a bit. Okay. That's a fine picture. I make a screenshot and I crop it a bit. Okay, that the first plane. And I also want to do a pressure field, okay? Because pressure is now a bit more interesting for us. And we take the static pressure. And here, let's have a small look. Now we have about 1 bar. Here at the entry, here at the exit, we have 1 bar because that's the boundary condition we chose. It should be, of course, 1 bar. So in this region here, the pressure is a bit higher. And that's because the velocity of the water hits this region here. And okay, so I want to have a look how high the pressure gets here. And here we have a pressure of 10,003 Pascal. We have a pressure of 99 Pascal. Okay. Maybe I have to check if I took the right medium, because I think this is air now, but normally I wanted to choose water. Let's check it. A small look. That's a problem. Normally I took air, but that was not right because I want to have an incompressible medium, and air is compressible. That's not what I wanted to do. So go to solution, clear data, clear generated data, update it again, make a new simulation, refer to the monitor points. Yeah, and probably convergence is even a bit better. Yes, this a gas is always more complicated to simulate because it's compressible. Ideal gas law has to be solved, so it's better to take water to measure the pressure drop in this pipe. Okay. So I think we can delete this picture and this picture. We don't need it anymore. And now we have a look in our result file. Okay, now you see a much higher pressure drop, and if I pick the pressure, first I make a screenshot. Okay, That's better, and you see the pressure difference is much higher because we don't have a compression in the gas. We have an incompressible media and a high pressure drop. So we take this value, it's a value of, I just go to Excel and I copy this value. No, that's not what I wanted to copy. Copy. So it's pretty fine. I'm sorry, we have a German Excel. We need a comma as decimal separator, and we have delta pressure about 2666 Pascal with the first geometry 12. Let's save it. It's always important to save it. Okay, and now we come back to our results. Maybe let's make a small picture of the streamlines. Okay, pretty fine. Oh, but it's not so fine. Can be a bit better. We do it like this. Okay. Looks fine. And let's create the next pipe section 13. This is pretty fine. It looks good. And I go to the I rename it here. Pipe simulation number 12, and now I duplicate, I save it, I duplicate this workflow. It takes some time. I rename it to 13. And I go to geometry, I edit it, Okay, and I think I did a mistake. I tried to edit it in space claim. That's not what I wanted to do. I think I have to do it again. I wanted to choose a design modeler. I don't want to use the space claim. It's a good program, but I don't want to change anything in the workflow. I want to close the space claim. And I want to edit it in design modeler, because I don't want to make big changes in the tool. Okay, here again we have a swap. We look at our next exercise. It should be now a round pipe, and it should look like a T, and it's also easy to do. I take the first plane here, and I go to my sketch. I delete the swap. Okay, I delete this one. Outlet, inlet, delete the swap. Go to the sketch. Also, this is something I can delete. Go to the sketch. I want to delete it, and I want to now I want to paint a circle, and the circle should have a radius of the same 25, and the area would be a bit, let's take 50. Looks a bit better. I take a 50. It doesn't matter. It will not change anything on the pressure drop coefficient. And now it's more easy. I just can take a extrude and take the sketch. I extrude it in one direction, and now I extrude it in reverse, both sides. Symmetrically, and make it a bit longer. Or what do you think? Should it be longer? Yes, okay. Let's take 150. A bit better. And now we go just to the other plane. Again, we sketch a circle in the middle. This. We take a dimension, a radius, like this. We choose 0.5 as the radius. Go to generate, extrude, 150, apply. And we have done our geometry of a T. It's a bit short. Let's do it a little bit longer. Go to this extrude, and I do it maybe 2 meters. Better. Extrude those to 2 meters. So, okay, looks pretty nice. Looks like the same as here. And now this wall is closed, and we want to choose this as an inlet, named selection, apply, generate, rename. No, this is not really cool. Inlet. Okay, and we take the next also as a name selection, and we call it outlet, and it's finished. We'll check it, inlet, outlet, and here is a wall. We close the brush drop, go to save, we start the meshing, update it, and I'm pretty interested if we now generate also hexaedral mesh, but I don't think so. I think this mesh will be tetrahedral mesh because it's more optimized to these round geometries. Okay, let's wait a second. Here we can look at the progress bar, and it takes some time. Here are some messages. Okay. Maybe we want to edit it and open it. Okay, there's no mesh. No geometry is selected. Okay, that's clear because I changed the geometry. Again, I have to choose my pipe, and now it should be defined. If I delete the geometries, ANSYS can't know all the details, and now I have this nice tetrahedral meshes. That's what I wanted to choose. That was my idea, because it's really hard to mesh a pipe with a hexaedral mesh. And I do a screenshot, I enter it here, make it a bit smaller, crop it. And my next pipe is finished. Looks pretty cool. I want to save it. I'll just close the mesher, update here. And make sure that you have placed the outlet on the right side here on this entry and not here, otherwise we'll have another result. I go to setup, don't need this error messages anymore, and here it is. My mesh looks pretty good. I choose the inlet, and now make sure you are in the right direction. This is Z plus direction, so we have to choose a W minus velocity. We have to make sure that we have water. We have to make sure that we have a right outlet, and here should be a pressure. And here are some walls. I want to delete this feature. I go to default, rename it to wall, and we're finished. Solver control, 100 seconds, and I think that's fine. Maybe check it a bit here, close it, save it, delete all the old datas. Clear the messages, everything was fine. Go to update of the solution, And probably this can take some minutes or some seconds. I want to check it. I look at the task manager. I only have one CPU for the simulation. Mesh is a bit bigger. And I go to the solution monitor. So, but it's a fast simulation. Of course, a little bit slower than the other simulations, of course, because it's a much more mesh cells and it's a tetraedral mesh. And we only use one CPU, CPU 9, but it will take, I think, about 1 minute. We can wait a bit for the 100 iterations. Convergence is still okay. It's not so low, but doesn't matter. Let's wait for a while. But we can have a look at the memory of the computer. Yeah, about the memory. CPU is okay. Network traffic, a bit high. CPU 9 has to do all the work. We have no parallelization. All the other CPUs are idling. Later we can try out a simulation with more CPUs than one. It will be much faster, and we can also parallelize the simulation, use the other CPUs. Let's have a look at the memory. It is okay. We have about it's not what I wanted to do, but it's time to do it. And we are at iteration 95, 96, 97, 98, 99, and iteration 100. Convergence is reached. Congratulations. Simulation is finished. We can close it. We can edit the results. Have a look at our fluid flow, and that's how it should look like. Perfect. Make a screenshot. Copy it here. So okay, looks fine, but it looks realistic. We see where we have the turbulence, we see where we have the swirl. Here's not much happening, not much velocity. We see the maximum velocities, but now it gets pretty interesting. We want to check the pressure drop. Here, it's the wrong plane. I want to change the plane a bit. That's perfect. We have to pick the pressure here. It's about take the pressure drop at the entry. Let's check again how big it was. Okay. Right. Okay. And the exit is like this. And you see delta P is much smaller than this delta P. Have a small look. It should be here 4.5, 250. Looks, makes sense. Saves this table. And I make a picture for our slides. Keep it in mind. Make the picture. Crop it. Okay, I'm in the middle of the slides and I think now is a time when I want to close this lecture. I don't want to tell you too much about the solution. You can try, look at the formulas here, look at the Excel sheet I started to do, and look at the PowerPoint I started. Look at the workbench. I think you now can follow up the steps and finish this exercise for our pipe 14. So please do it on your own. Enough help for now. Have a good time. See you later and bye bye.